No, not specifically.
Okay, so welcome everyone to our first Nexus talk of the new quarter. Welcome back. And today we're kicking it off with a very senior, distinguished visitor, Yara. And how do I say your surname?
Mohajerani. It's okay if you don't get it.
Mohajerani, with difficulty.
Yeah, there you go. Oh, that was good.
Homegrown, we'll claim, right? Even if he did come from Canada. But he got his PhD only in December 2019. He's already co-founded two tech startups. And at the moment, he is CEO of AI Solutions, Inc. And so what we're going to hear about is a mixture of academic and sort of entrepreneurial sort of stuff, I think. But we're going to learn about the machine learning part, especially, and what it means for global observation, I would say, right? Okay, so take it away, Yara.
Okay, well, thank you for the introduction. And yeah, happy to be giving a talk at UCI. Wish I could be there physically, but this is as good as it gets. So yeah, today I'm gonna give a bit of a broad view first on machine learning satellite observations and the cryosphere, and then go into some of the more specific research that we've been doing. And this is mostly gonna be just on the academic side and sort of the publications. Okay, so let me minimize the Zoom window here. So as some of you on this call may know, there has been sort of an explosion in observational data in the geosciences. And we have a fleet of satellites launched by both government agencies and private companies like Planet. And it's kind of transforming the way we do research in the geosciences. So up until now, a lot of the bottleneck in understanding what's going on with all of geophysical processes was just a lack of data to get representative data of a lot of physical processes to then formulate. And now that's kind of shifting to just the data is there, but a lack of processing to understand what's going on. And to give you an example, the ISAT-2 satellite, which was launched not that long ago, produces just under 1 terabyte of data per day. So every day, it's about a terabyte of data. So that's kind of the scale that these days we're working with. So at the same time, many of key glaciological processes are still very poorly understood. So a lot of glacier dynamics, marine ice cliff instability that I'll talk about, a lot of the stuff that I spent my PhD in Irvine trying to understand on the sort of science and physical side are not well understood. So this is the infamous case of the Larsen B ice shelf that collapsed at this point a long time ago. And there are still papers written on it on like what exactly caused it, what leads to these processes, what exactly is the mechanism behind it. And to be able to understand these sort of key dynamical events, it's not enough to just get one case study and look at it and make a whole physical model out of it. You need comprehensive large-scale observations that really span the ice sheets spatially and temporally. So before going too much into the nitty-gritty, I want to also motivate you a little bit more about why any of this is important, just on the broad science side. So again, as many of you may know from the climate change side of things, there's a significant mass loss of glaciers worldwide and on the ice sheets at an accelerating rate. So Antarctica, according to a recent paper by Eric Rinio at UCI, was losing about 252 gigatons per year of ice, which is a lot. And Greenland, it's negative 286 plus minus 20 gigatons a year. These are big numbers in recent years. And this is only accelerating. And this has huge global consequences, of course, with sea level rise being one of the most noteworthy, affecting millions of people, as well as other side effects. Um, and just to motivate you a little bit more before I move on, these things are still very uncertain, even though we know that, we know a very good amount about them, but there's a lot more to go as well. So these are some of the sea level projections under a fixed climate scenario. So what's called the RCP 8.5, fixing everything else, just the uncertainties in the actual glaciological models. And if you look at the median in the black line, and then the spread for sort of roughly 1 sigma, 2 sigma, 3 sigma, it's actually the 95th percentile, and I believe 0.199 or 199 percentile. But more or less, you see the huge spread, the long tails, especially on how big potentially sea level could be. And most of that uncertainty is coming from the ice sheets, mostly from Antarctica. And again, this is just our lack of understanding in the physical modeling of the glacier side of things, not even, it's with a fixed climate, fixed climate forcing. And this affects a lot of people. So 153 million people could be displaced by 2100. That's a lot of people. On the economic side, you could have up to $1 trillion per year worth of loss in terms of flooding by just the middle of the century. So we really want to kind of narrow down these margins and figure out exactly what's going on. So that's kind of a big picture motivation before we move on. And so in this talk, I'm going to focus on two of the key processes that I've focused on, especially with this angle of sort of data science machine learning approach. One is glacier calving fronts, which is sort of just the front wall of the glaciers where ice breaks off and calves off, goes into the ocean, and glacier grounding lines, the point where glaciers start to actually float in water and no longer supported by the ground. And I'll talk about each one in more detail. So each one was sort of a project that was published, one in 2019, one more recently this year. And I'll kind of go through some of this stuff that we've done. So first to start with the calving front, this was the sort of more smaller scale initial project that we did at UCI. And calving fronts, so again, this is the front wall of the glacier where it breaks off and calves into the ocean, forming icebergs. And it's really important to delineate these fronts over time to get a better understanding of the dynamics of glaciers. So for example, Mike Wood, another UCI graduate who's at the JPL now, did this study showing how when the seasonal range of the calving front migration, when the migration goes beyond a certain seasonal range, it actually leads to retreat due to undercutting by the ocean. So but this kind of research is done by manually delineating tens or even hundreds of calving fronts from pictures to be able to get a better understanding of the science. And again, so far, up until at least recently, to just look at like, kind of more or less hard code contrasts and gradients and images to figure out where the boundaries of glaciers are supposed to be. And there's some good results, but there's a lot of issues with this kind of typical analytical approaches. And when I say analytical, I just mean not in the sort of like the more old school kind of hard-coded approaches. Ways, and at the end of the day, it doesn't even give you the entire profile of where the front of the glacier is. It just kind of gives you a statistical position as a point. But at the same time, I think we all are aware that there has also been a huge boom in sort of computer vision and the whole boom in machine learning, which is the bread and butter of the ML Nexus group. So I don't need to justify that. So yeah, I mean, semantic segmentation, is a huge field. Doing pixel level segmentation, anything from self-driving cars to anything else. And this provides the perfect framework to kind of revolutionize the geoscience side of this and actually get some science out of this vast amount of data that we don't know what to do with. So very roughly, I'm sure you all know this, but yeah, the perfect way to do this, we're not really interested in sort of classifying whole images as like a image to vector kind of approach, but we just want to utilize the fully convolutional network to go from images to images with the desired kind of boundaries and features kind of brought out. So the way that I initially approached this in the 2019 paper, UNet is sort of everyone's go-to with these kind of problems initially. So it's sort of a modified UNet approach with, and so the encoding component and the decoding component. And I'm sure I don't have to explain this too much, but there's basically the encoding side where you have a series of convolutional layers and like max pooling layers, and you kind of get you learn the features that you're interested in the image, and you kind of you could think of it maybe from a mathematical side as like dimensionality reduction. You really get the dense representation of the features you're interested in, and then in the decoding stage, you can think of it as building the image back up into an image with just the boundaries you're interested in. And of course, you have the skip connections that also transfer more of the contextual kind of spatial knowledge with the dense feature information that we've put into the encoded layers that gets passed on, and through a series of upsampling convolutions, you get an image that has the glacier boundaries and hopefully nothing else. So that's kind of the idea. And so, UNet was first kind of made for biomedical stuff, for finding boundaries of cells, but it works just as well for, it could be satellite images instead of tiny little cells. And of course, there's a big class imbalance, right? Most images have only a few pixels that are Calvin fronts, and most are not Calvin fronts. So initially, the way I did that in this initial approach was to dynamically, for every image in the training, automatically have a matrix that corresponds to the penalties, right? The false positives versus negatives. But instead of just hard coding that into the loss function, we actually had a dynamic matrix that was also inputted with the images that corresponds to the weights, according to which pixels in the training data are Calvin fronts versus not Calvin fronts. And that ratio for one pixel type versus another were just the mean ratio in the training data set, in the training labels of the number of non-Calvin front pixels to Calvin front pixels. So with that, the sort of pipeline that we set up back in 2019 was taking these geocoded Landsat images. And initially, this was sort of a pilot project. We didn't want to, spend too much time on the training and like augment too much in the orientation. And this was actually just trained on the infrastructure at UCI on CPUs, so not even using any fancy GPUs or anything. So kind of a lot of the effort was gone into the pre-processing to orient everything in the same direction, so we didn't have to augment and spend a lot of time training and pre-processing. So all the sort of contrasts are more or less similar across images and the distribution of the grayscale, and then feeding it through the CNN, getting a raster output, and then vectorizing it, and I'll talk about how this post-processing is done, and then putting it back into a geocoded data set. So then once you have this, you could get, hundreds and thousands of Landsat images and automatically get all the time series of the Calvin fronts and do all the amazing science that you want to do with it, like the work that Mike Wood is doing. So we focused on 4 regions across the Greenland ice sheet. And we actually, one thing that we specifically wanted to test was not having any fixed resolution in the data. So 3 of the glaciers that were used for training had pixelations anywhere from about 60 meters to about 90 meters. And then we tested it on the higher resolution data set with each pixel being about 49 meters. So this is sort of but we brought everything down to 200 by 300 pixels, with each pixel being different resolutions for different images. And the sort of glacier fjord that we tested on was none of the images from that was used in training. So not only new data, but a whole new geometry and glacier fjord for testing. And actually not a whole lot of data. So 123 pre-processed tiles, which is very, very little when it comes to machine learning. And surprisingly, it worked. You could say, you have to be careful about overfitting with cases like this. And I'll talk about some of this. And then the next projects that we did kind of address those questions. But yeah, so we also did some augmentation just to increase the variability, mirroring the images. We also experimented with flipping them vertically. That didn't seem to do too much, so we just stuck with mirroring them. And then just setting 10% aside for validation, and then test fjord. And then importantly, we also had the truth labels so the original Landsat data is far higher resolution, right? It's about, if I'm, and even our highest resolution test site was still about 60 meters. So everything is down, interpolated to a lower resolution anyways, but the true fronts, when I say true, in this case, like an even resolution that was given to the neural network to the other hand delineations that are done on the high resolution to compare the results of the neural network to what the human would do on a similar resolution. And also a quick note on the post-processing. This problem of vectorization is always a tricky one, and I'll come back to it. But in this case, it's easy because we kind of have these two fjords, the fjord walls that determine like the lateral boundaries of the glacier, and we kind of used a least cost path through the boundaries, through the points that were highlighted by the neural network to sort of get a vector output for where the most likely position of the calving front is, and then convert that to a shapefile and just save it as a line. So results, we actually got results that were very comparable to human performance, which is really good. So again, as I said, we are comparing both machine learning and human errors to the truth labels, with the truth labels being human delineations at a much higher resolution data. So the human error is about 1.89 pixels, whereas the machine learning is 1.97 pixels, which is pretty good. And interestingly, if you look at the distribution, this is a pattern that we see over and over again, at least in the stuff that we've done, where the human delineations are all sort of crowded in the vicinity of the quote unquote true answer, not too close, not too far. And then machine learning output could be much closer, like the peak closest to zero is very big, but it could also have big outliers where it gets completely fooled. And then the analytical filters, we wanted to compare with some of the older methods, like the Sobel filter, and that could just get it completely wrong. It's very susceptible to noise when you have like, icebergs in the front. And so you get these huge outliers sometimes. So this was published back in 2019. This is all UCI people at the time, with Eric and Isabella at UCI. And since then, UCI is still taking the lead on this. So Daniel Cheng, who's also in the computer science department at UCI, has expanded on this work, and I was lucky enough to be a part of this as well. The calving front machine, or CalFin framework, and this was recently published in the journal The Cryosphere. And this kind of takes this to the next level and uses a more kind of updated architecture based on the DeepLab v3 plus architecture, and kind of goes through the entire coast of Greenland with very good results. And at this scale, this is just ready to be used for modelers and like scientific, real scientific insights into what's really going on. So this is something that's in progress, and UCI is in a good place when it comes to this and pushing the field forward. So the more recent project, and kind of the bigger one, and the one that I'm more excited to talk about, is this grounding line delineation. So the first study that I talked about was sort of like a teaser pilot project, and then this is where we kind of went to the bigger scale. So grounding lines are, as I said in the beginning, the boundary where glaciers go from just sitting on the hard ground to being basically just floating on water. And this boundary obviously changes with the tides, right? As the water level goes up and down, you can imagine this boundary goes up and down. So that range is called the grounding zone. And it's it's a very important dynamical parameter to know for scientific purposes, because it kind of directly informs you about the ice-ocean interaction that derives so much of the mass balance processes of glaciers. If you have warm, salty water kind of eating away at the bottom of the glacier, what really tells you what's going on is the position of the grounding line, and not necessarily how far this ice shelf goes, which is more about the calving front that I talked about before. And this leads to some other very sort of much talked about concepts in glaciology, which really dominates a lot of the conversation about sea level projections, is marine ice sheet instability, where you can imagine a lot of these glaciers sit on retrograde slopes where the slope is away from the ocean. So as the glacier is kind of eaten away by the warm water, you get a positive feedback where more and more warm water gets in, eats more of it, and then even more, and you just end up losing a whole large chunk of mass, and sea levels go up. And this is kind of a runaway effect. But then to be able to kind of analyze these things and know if it's going to happen, how much it's going to happen, you need to know where the grounding lines are. And this is a very hard problem. And it kind of ties back to, if you remember in the beginning saying hundreds of millions of people might be affected. This is the kind of thing that will tell us how exactly they're going to be affected. So how do we go about this? So this is notoriously hard to kind of figure out, because in this kind of schematic, you could kind of imagine in the black boundaries, that's the glacier. And from the top, there isn't much you could kind of see. Really, all the action is happening at the bottom, where it's no longer supported on the seafloor. So if you look at images, like the way we did before, you can't really see much. If you're like literally standing there, hard to tell in situ. So the way people usually do this is with NSAR, which I'll talk about in a second, to get a sense of this flexing zone. So by that, I mean, you can imagine as the tides go up and down, the ice shelf is kind of moving up and down. And this boundary is like a hinge that's always kind of flexing up and down with the tides. And if you keep track of the elevation, you can see that hinge just always going up and down with the tides. And the boundary of that hinge is exactly the line that we're interested in. That's the grounding line. And this is usually done by looking at this kind of complicated interferograms and manually delineating them in a very painstaking process. And there's plenty of people on this call that could tell you how painful that is. So just a quick note to understand the data that I'm talking about on NSAR. So NSAR is like its own field, and I'm by no means an expert in it. But just to give you a very kind of, bird's view view of what's happening. So the idea is kind of keeping track of the phase and amplitude of radar waves kind of being bounced off the surface, right? So I can imagine one satellite going by, you have some radar pulse being reflected, and then imagine the ground moves in between the time where the second pass happens, and a different phase of the radar is now reflected, right? So forget about the travel time, just look at the phase of the radar. Because the distance is changing, a different part of the wave actually gets reflected off. So by looking at the phase, you can actually get a much better sense of the height change than if you just wanted to keep track of the time, let's say. So in reality, it's even more complicated, the data that we have, because we use 4 passes. Because in this case, you could have both horizontal and vertical motion between passes. So by using 2 pairs of interferograms, basically, we account for any horizontal velocity of the ice and just look at the topography. Anyways, that's not really the point of this talk, but I just want you to understand where we get these patterns that we're going to see. These correspond directly to sort of going between 0 to 2 pi of the phase. Each one of them, if you want to think of it as heights, if the wavelength has a unit of 1 in whatever units, then 0 to 2 pi would be a unit of 1 in terms of height change. So that's just basically cycles of the phase translating to height. It's okay if that's a little confusing, but the point is these fringe patterns actually directly correspond to height changes, which you can think of as sort of, you can unwrap them, and instead of 0 to 2 pi, you could just continuously increase or decrease as height. So what a human would do is to look at these fringes and figure out, okay, where exactly is the boundary of that hinge that I'm interested in? Now, this is a much different problem than what I talked about initially with the imagery. And sort of the imagery problem is a lot more commonly used. It's in different fields. So, you know, like I said, it could be medical or biomedical imaging, self-driving. This is a much more unique problem in some respects. And, you know, for one thing, if I take an image of a glacier and kind of just crop it into the very just boundary of the glacier, you could look at it and still tell that, okay, this is where the boundary is. If I zoom in on this, you can't really tell what you're looking at. It's very context dependent. If you're just looking at this little part here versus this little part here versus here, can't really say. It's the whole thing that puts the meaning to it. And it's also super noisy, right? You could have decoherence where you get noisy kind of patches in your data. You get different textures. It's again very context dependent, and it's very, the context is also the textures and the context are manifest themselves at various scales at the same time in this kind of data. And just on a technical side, this was also a much larger data set that we were dealing with and ran into all kinds of memory issues that I'm happy to talk about after, which was interesting. So to address a lot of these problems, we kind of changed the architecture of what we were working with here. So I kind of really relied on doing this multi-scale, multi-spatial scale processing in parallel in this case. So this is also very inspired by the DeepLab v3 type architecture, where you start as usual with a series of convolutional layers, dropout, convolution, max pooling, and you kind of keep getting more and more dense features. But then using a series of sparse convolutional kernels, so like sparse matrices being convolved, in other words, HRS convolutions, in parallel, we can kind of sample the image in multiple different scales, right, in parallel. So this one is just the multiple of 1. It's just, this is a regular convolutional kernel. This one misses every other pixel, but it has a field of view that's twice as big, 3 times as big, up to 5 times as big, all in parallel, stitch them back together, and then feed them back to the decoder to make the image. But then the number of parameters could easily explode in this and just spend way too much time training. So we also do depth-wise separable. So assuming there is no relationship between, you could think of it as like cross correlations, right, in depth and width. We kind of say, okay, let's just do the width and then the depth-wise. We actually tried doing depth-wise separable for all the convolutional layers to just increase the training time. Doesn't work so well. So there's some sort of structure there that we want to conserve. But doing the depth-wise separable convolution for the HRS convolutions that actually works really well. And then putting them back together, like I said, and building the image back up. And in this case, we also didn't necessarily want to impose like the unit, a perfectly symmetric encoder decoder. It doesn't really matter, right? We wanted to spend a lot of effort kind of sorting through all this noise and spatial stuff that's going on at multiple scales. Once you have all that information, you can kind of just build it back up. It works if it, don't have to rely so much on the symmetry. And then, yeah, on the technical side, and this code is all on GitHub. You could check it out. We had to kind of make our own makeshift data generator classes to feed into the Keras trainer and like deal with some of the bottlenecks in data that you can check out later. But the pipeline, basically, our training set was about 6,000 geocoded tiles of these interferometric tiles. And first we delineate basically rasters for where the grounding line is with the neural network. And then we stitch all the tiles back together into the bigger interferograms so we can vectorize them, because you could have lines that go across different tiles. And this vectorization problem, basically, we made polygons. We vectorized it by drawing polygon contours around the pixels that are most likely to be the grounding lines, using a probability of 30%. So using a threshold of 0.3. And that has two. One is you get vectorized results, which is what you were interested in. But also, this has a unique advantage of giving you uncertainty estimates. If you sample the probability of the pixels that are likely to be grounding lines and you kind of draw contours around them, you get a data set that also tells you with different levels of probability that you can input to the pipeline what uncertainty you want to use. And this may seem kind of trivial, but on the scientific front, this is important because none of the previous, there's a lot of these delineated data sets that are hand delineated, and none of them have uncertainties. And that's a big problem for the modelers. And this sort of approach readily gives you that, which is just the added bonus. And then lastly, we just want to draw center lines through the polygons. And sometimes that's a bit more tricky than it seems like, because you could have all these like tributaries going out. It's all these little complexities actually turn out to be much harder. But this particular module actually worked really well, the labeled centerline module, which again, you can check out the code. I can link to it at the end. So the pipeline performance, so you can kind of see the pipeline here. In the first panel, panel A, in white, those are the hand-drawn delineations of the grounding line, and that you can kind of see the whole interferogram here. It takes a while to get used to the nature of the data, but you kind of see the fringes here where the flexing zone is. And these are the raster outputs of the neural network. And I'm assuming you can see my cursor, but let me know if you can't, because I'm kind of pointing to things. Okay, cool. And you can see they have different widths. So that's, areas that are more noisy, more pixels are likely to be grouped in together as a grounding line, and that's useful information, right? That's the uncertainty. And yeah, the grounding mask is the test site that was not seen during training. So these are brand new areas within the interferogram. Because the tiles are all shuffled, so an individual interferogram could have patches that were trained or test data. That's where this mask comes in. And then here you can see the vectorized output of the neural network. And some of the things to kind of just point out is you could also have these pinning points. You can imagine the ground kind of coming up like an island, and the ice gets stuck on that island. So you have like a little point where the ice is grounded again. And just on a technical side, then vectorizing these things is also a pain because it's very different than drawing center lines through polygons. And I'm saying this for a reason, because we're hoping to move to a vector embedded output, which I'll talk about at the end. But it's good to keep these kind of difficulties in mind. So zooming in on the red rectangle here in this area, I could see the white as the manual delineation, and the dashed lines are the uncertainty, and the center line is the solid line, and the human delineation is within the uncertainty bars. And this is just one example, but this is actually true in all cases. Our human delineations are always within the uncertainties of the neural network, which is fantastic. And in fact, we get a mean uncertainty estimate just from the polygon widths of about 4.5 pixels, which is 451 meters. Each pixel is 100 meters.
Sorry, Yara.
Yeah, go on.
When you say the machine learning, the human is always within the machine learning uncertainties, is that like 1 sigma, or like what are the bounds?
Yeah. So so we actually, as before, compare the human performance by itself by comparing multiple humans. So some of the stats are here where if you compare multiple human delineations, even with a single human on different days, the mean difference between those people is 268 meters on different days compared to a single line. Whereas if you compare the neural network to the human, to 332 meters, or 2.3 pixels. But in terms of the distribution, which what you asked, you can look at we looked at the mean absolute deviation and the interquartile range. The mean absolute deviation between the neural network and the human is about 1 pixel, but between humans is about half a pixel. And also similarly, the interquartile range is a lot smaller for humans. So this is interesting because the human mean differences are actually larger than the machine learning differences, but the distribution is also smaller. And this is exactly what we saw if you think back to the Calvin Coin stuff. This kind of keeps coming up. The human stuff is always around the right answer. It's never quite on top of it, and it's also never quite far away from it. Whereas the machine learning could be really on top, or it could just get it wrong, which is why the range is bigger, but also the mean difference is smaller.
But here you don't have sort of any kind of ground truth or high resolution data to.
No, there's just one kind of resolution in this case. But our truth is sort of, so we have a primary delineation, which was done just once for all the data, like beforehand for scientific reasons. And then we kind of took that as our ground truth. And that was sort of like, the one that was done really carefully by actually Barrington who's on this call. And then we just had people do it over and over again. And that was sort of the human test. But trying to doing it as carefully as they would. But yeah, it's just one resolution. So we can't really compare the ground truth in this case.
Right.
Yeah.
Okay.
But I mean, that is an important point in terms of consistency, because even though the human doesn't have the kind of larger distribution when it gets it wrong, whenever it is right, it's more consistent, which makes it easier to actually keep track of these features over time. Because if every day you draw these things by your mouse on the computer, it's like slightly different. You can't really then at the end of the day, okay, this time series is kind of noisy. Is that just because I drew it weird? Or, like, because these are like big physical features that you're keeping track of. And a little thing on your screen could be like, you think this glacier is going away, but it's not. So it's important to have this kind of consistent machine learning pipeline for doing these things. Yeah, and also the last thing I'll point out on this plot is in panel E, there's also portions where the human kind of misses the grounding line. So these are the ML only and yellow boxes. And then there's portions where the human gets it only and the machine learning doesn't. So these are the manual only. So this is interesting. So in most cases, they both get the lines, and actually it happens more often that the machine learning gets a line and a human doesn't. And that's only due to the fact that the way these were delineated, the human delineator had a much higher degree of caution. Like whenever it gets noisy, I don't want to risk it. Let's just stick with the objective, the best we can do. Whereas because of the way we set the penalty in the loss function of the neural network, the false positives versus negatives, we really forced it to just draw the line. But when it draws the line, it actually does a really good job. So if you look at the ML only, like over here or over here, that's right on the boundary of the fringes. And you can look in more detail, and the human expert can look at it, and it's good. So that gives us hope that this is actually doing a good job. But of course, there's some parts like over here or over here where the machine learning kind of misses some aspects, and you get that sometimes. And these could be adjusted. You can always go back and retrain with a different ratio of false positives and negatives in the loss function if you want to be less or more conservative. Yeah, and we kind of talked about this. So then moving on to sort of understanding a little more what's happening here. So looking at the activation maps, which kind of tells us what the kernels are actually picking up at different stages of the pipeline. So one thing that was curious to me before even getting to this was, if you go back to sort of these fringes, for example, here, if you just look at this, it's hard to tell which side is the grounded side and which side is the ground and which side is the ocean. Right? If I just show you this with no directional data, I see the fringes and I know that part is like going up and down like a hinge, but which side is fixed on the ground. Now there's of course subtle things in there that a human expert could tell you, like the patterns are a little bit different. To be honest, right now, I don't know which image, which side is which, but I'm not a entire expert. So, but I'm sure like if Bernd on the call looked at us, he could tell you. And it was interesting to me how the neural network got this, because we don't give it any directional data. So even sometimes the humans have to go look at the velocity data. Like, oh, the glacier is moving, whatever, like in the down southwest direction in this case, or whatever. So I know that side is the ocean. But we didn't have any directional data for the machine learning. So how does it tell? So that was kind of the reason I started looking at the activation maps, but they're just interesting nevertheless anyways. So going back to the idea that you're looking at the phases and amplitudes, right, of the radar, you can also think back to like Euler's formula. You can show that as real and imaginary components, right, instead of phase and amplitude. So these are the two input channels. And you can kind of see how noisy they are. Just looking at layer 5, so just a couple of convolutions in, you could see the activation maps, what the kernels are picking up. And it's just picking up features all over the place. There's like this blob in the middle. There's like large scale, small scale features. It could keep going. So going all the way to layer 16, right before the parallel HRS convolutions. it's actually picking up the grounding line, but it's picking up bits and pieces. It can't really take the whole image in at once. And really the key thing comes in as soon as you do these parallel HS convolutions to like bring all these multiple scales together. All of a sudden, bam, the whole grounding line just pops out. And that one more step, right? Going from 16 to 22. And this kind of really shows you how like the multi-scale nature of this problem is addressed by the parallel HS convolutions. And also going back to this problem of the size of the flex, the side of the flexing zone, these are clearly asymmetric activation maps around the grounding line. So just looking at this, it doesn't convey any information like to me as a human, like what this means internally to the neural network, but it's not treating two sides the same. You have these asymmetric activation maps in all the kernels that we looked at. So it's kind of encoding that information about the direction in there. And just a quick note on the training time. So both on the what I talked about initially with the cabling fronts and the grounding lines. So the cabling fronts, like I said, the initial pilot project was all just like CPU training on Green Planet. Didn't really at that point even have a good time estimate on how long it takes. But then on the Calfin project, we did a rerun of the unit structure we used for that 2019 paper. And on a Tesla K40 GPU, it takes about 21 minutes per epoch, which we had before about 60 epochs, you start to overfit. So about 21 hours of training for the cabling front. The grounding line, it's one less input channel, so 2 instead of 3, a lot more data though. But it also needs a lot less epochs before you overfit. And each epoch takes about 10 minutes on a Tesla P. We did it on a Tesla P100 on Google Colab actually. And the whole thing takes about 1.5 hours, which is really good. And then once it's trained, then it's super fast. It's milliseconds per image to just delineate things. So let's see how I'm doing on time. I have a bit of time. Okay. I'll just quickly go through a little bit of the results in the science and the future outlook, and I'll wrap it up in about 5 to 7 minutes. So given that pipeline, we kind of went ahead and delineated all data from Antarctica in 2018. Every single interferogram from Sentinel-1 A and B with 6-day or 12-day intervals, which amounts to about 23,000 interferograms. And you can see the distribution of them for 6-day and 12-day intervals all around Antarctica. And it took about 17 milliseconds per tile. And these are 512 by 512 12 tiles. So the whole thing takes about 21 hours in total. Now, to give you a sense of how much this changes the science progress of this, we kind of extrapolated, given the average time it takes a human, this would take about 7,600 hours to go through this much data up until last year. So all of a sudden, this kind of revolutionizes what you could do with this data on the analytics side. So just looking at a few points. So again, this is all of 2018, and you can see the grounding lines kind of as a function of time throughout the year. And looking at a point on the peninsula, West Antarctica and East Antarctica. What I just want to point out quickly here is you could see the grounding zone, right? Like the changes in the grounding line over time, which is just because every time you're sampling at a different tide. But then if you look at the uncertainty of 3 randomly picked lines in the beginning, middle, and end of the time span, what I just want to point out is the uncertainties are in all cases smaller than the actual width of the grounding zone, which makes it meaningful to actually look at the movements over time to get the grounding zone, because the uncertainties of any individual line is smaller. So with that, I'm not going to spend too much time going into the weeds with the glaciology stuff, but just a sort of big takeaway. We have these observations now of how wide this grounding zone should be. And we see from our observations, delineations, that it's about several kilometers wide. But we could also calculate this theoretically just from simple hydrostatic equilibrium, assuming a hard bed and solid ice. And there was this paper in 2015 by Tsai and Goodmanson that kind of went through this. And basically just depends on the bed slope of the glacier, surface slope, the tide heights, and the density of ice and water. and you could get the width of the grounding zone given hydrostatic equilibrium, which is what I'm going to denote as the kind of HE delta L, HE being hydrostatic equilibrium. So, very simple calculation. And we also have, obviously, our machine learning delineation. So we can compare the two. How does the theory compare to the observations once you get access to this massive amount of data? And surprisingly, what we observe is about an order of magnitude larger than what the theory tells us. And this is not the first time that this has been pointed out, but this is the first time that at such a scale, it shows that, yeah, it's an order of magnitude larger than what it should be. And just on a quick technical note, the way we get the width of the grounding zone is, so we have all these grounding lines, these shapefiles that are produced, and in areas with slow velocity, so the blue shading is the velocity, areas of this slow velocity, we just use a geometric approach of fitting a perpendicular line to these perpendicular transect to these grounding lines. And in areas of fast velocity, we can actually use the direction of the velocity to just draw that transect, because where ice is moving in the direction. It's the velocity of the ice, anyways. So then we can compare the two. And yeah, the hydrostatic equilibrium is in the orange distribution here, and machine learning in green. And 13.3 plus minus 3.9 is the ratio of the ML width versus the hydrostatic width. This is very interesting, right? It's something is not as we expect. And again, this is not the first report of this. And this is also on a particular region, the Gates Ice Shelf in West Antarctica, where we had the best data. So we know we are getting like the best machine learning delineations. This is trustworthy data. So there have been some previous theoretical studies that have predicted that, okay, if you use not a hard bed, but a deformable bed, you actually do get wider grounding zones. Or if you model the movement of the grounding line as a propagation of an elastic crack at the grounding line, it actually also leads to higher grounding lines. Now, I'm not a theoretical modeler for glacier dynamics, so I'm not the person to ask about how these lead to those predictions, but at the very least, it's interesting that what we observe actually ends up supporting these theories and not the kind of well-accepted hydrostatic widths. And sort of in terms of implications, what this means is that seawater is actually intruding potentially much further under the grounded ice at high tide. So it could actually melt it a lot faster. And if you think back to that kind of runaway effect potentially of like eating away at the bottom of the glacier, we got to really take that seriously. And if these grounding lines go all the way back when it's high tide, well, it's really eating away at it. So this has big implications for ice-ocean interaction and sea level rise. And this goes directly back to the modelers who model these things. And at the end of the day, all of this is to reduce that the long tails of the sea level projection that I showed you in the beginning. This is the direct kind of thing, the kind of thing that would directly kind of minimize, hopefully, those long tails by getting a better understanding of what exactly is going on at that boundary. Yeah, so this was published not that long ago, again, with the UCI group in Nature Scientific Reports. And I'm very proud of this work. And I think it's a good direction for the field as a whole to kind of start taking this massive amount of data seriously. And I just want to quickly talk about the future steps and then open it up to questions. So the next obvious step to go with this is both for the grounding line radar stuff and for the image-based calving front stuff, is to start adding time dependency. So right now, every image is added as just a completely independent input, right? But when a human looks at it, if you're kind of lost, the data is too noisy, you just go one image back in time. You're like, oh, well, the line was here. It can't move like 100 kilometers in a day, right? So I know where it should be. And then I can go and like figure out, okay, in this realm, I can figure it out. Right now, the neural network doesn't have any temporal dependency, right? It has no continuity over time. It has no knowledge of where it was just one step before. So the obvious step is to use either like recurrent neural networks or some sort of a transformer model to actually add that memory into the system of keeping track of the temporal continuity of the lines. And even on a more kind of longer term vision is, so I mentioned a couple of times that really the thing that slowed us the most probably, both in terms of just figuring things out while we were doing this and also just like the actual amount of CPU hours that go into this and the computational cost. It's not the machine learning and the delineation. It's always the post-processing. It's just the most annoying step. It takes forever. You got to get all these images. We have so many of them, and you got to like figure out ways to convert it to some sort of clean vector output to do everything else from there. And it would be the obvious step is to somehow embed an actual semantic understanding of geometries in the neural network. So you're, instead of just doing raster stuff with CNNs and then doing some stuff afterwards, just work with geometries and say, okay, I'm predicting a line here, a circle here, whatever. And in that case, maybe you can even start imposing constraints, right? Like one problem right now is there could be like little discontinuities. Like you have a long glacier and for some reason it just breaks in the middle. It does one line segment, then you got to figure out, okay, how am I going to connect all these? If you just force it to be continuous, then it's going to try to be continuous. Like you could do so much if you're working with vector geometries, which are these things are in nature. And there's some kind of starting points potentially, right? There's like graph to vec, there's pointer networks, there's all kinds of different things in literature that might be helpful, but I mean, I haven't done anything with respect to this vision. It's just something that I want to do. So this is more of a discussion point of like, you know, if anyone here has any pointers or any thoughts or discussion, I think that would be the biggest change, not just for this project, but just geoscience in general. Every single paper from ocean stuff to like getting snow outlines to whatever, everyone has this problem of raster to vector. How do I do that without messing everything up? That would be the biggest change. And yeah, so I'll leave with that. And oh, it says code and data available soon. It's actually available already. You can just scan this, it'll take you there. And yeah, acknowledging UC Irvine, Renew Group, Isabella Veliconia was my advisor at UCI, so thank you to her. And yeah, I'll open it up to any questions.
Well, thank you very much, Yara.
No problem.
I don't know, maybe if you stop sharing the screen for a minute,
Sure.
so we can see everybody. So do we have any questions?
Hey, Yara, I had a question.
Yeah.
On your
Sure.
grounding zone width comparison graph on with kind of like the blue sliding velocity sort of smudges, which side was like ground glacier and which side was ocean? I was just kind of curious looking at that.
Here, let me just maybe share my screen again. I'll show the whole screen. So you're talking about this one?
We can't see anything yet. Maybe that's just me. Oh, okay, it's back.
Oh, okay. Do you see my screen?
Yeah. The one on the I think it's slide 33.
Oh yeah, okay. So the bottom left portion is the ocean and the upper right portion is the ground.
Got it. Okay.
But I mean, you see the velocity continuing to the ocean, which might be what's confusing, but that's because we're looking at the grounding line, right? So the ice doesn't end, it's just no longer supported by the ground here. And it actually moves faster at this point on the ice shelf, it moves really fast. But so the velocity is there, but it's no longer supported on the ground.
Yeah, I was actually thinking the opposite. I was thinking that, you know, judging from this, it's, you know, fastest coming down from the top and then slowly going in the water, but, you know, so thank you.
Yeah, no problem.
Did I notice that you trained on Greenland, but ran it on Antarctica? Is that
no, so these were two, so the calving front stuff was in Greenland. So if I go back to here, so this was the calving front.
Okay. Ground line.
Image-based stuff.
Yeah.
The grounding line was all in Antarctica.
Okay.
So
Just
if I go, yeah. So we trained specifically, most of the training data came from this area. And it never saw like any of the other areas, and we just went all over the coast. Yeah.
And what do people make of this difference in the speed of, you know, about a factor of 10 of the movement of the grounding line?
The width, yeah, I mean, well, the paper just came out, so I guess we'll see what follow-up papers say. And, But but I know that this, I don't think is the first time that this has been observed. It's still something that, I mean, I actually did present this a couple of months ago at the Northwest Glaciology Conference, and I did get a few people who are like, few kilometers, that's crazy, like that would never happen. But I also know independent studies that do see that. So, but that's the point of having these large scale studies. If you can look at the whole ice sheet, then you're like, well, it's not just the one area. Look, I'm getting it everywhere. So
Right,
let's see.
right.
Yeah.
Yes. And so would you mind, especially since I think there's students and things here, would you mind commenting at all about how your entrepreneurial life interacts with your academic life?
Yeah,
what does the company do, the environmental AI one do?
Yeah, so basically I can stop sharing. So my goal was, on a kind of more philosophical basis, I spent a lot of time studying this kind of phenomenon and like writing papers on how bad things are, but I kind of wanted to do something about how bad things are, not just report on it. So I figured, okay, I do have the sort of data analytics skills and had some past entrepreneurial experience, and I just, it's important to me to choose the place where I'm working and not going to be bounced around all the time by academic positions from one coast to another, and be back in Toronto close to family. So it seems like the kind of perfect time also just in my life where I can risk it, worst case it doesn't work. And you have to be comfortable with the risk, which is very different from the, maybe from the usual mindset in academia, but you give it a try. And I would say the hardest thing is the bottleneck is almost never like technical problems. Any technical problem could be solved, but there's a lot of figuring out what you should tackle, who you should talk to, where the money is going to come from.
Right.
And so you asked what the company does. We've been working on a bunch of different problems. One thing that I've been thinking a lot about, and actually my co-founder is on this call too, is using machine learning and remote sensing and all these kind of paradigms to improve waste tracking, because it's such a huge problem where like a lot of recyclables just end up in the landfill, and like nobody can keep track of these things, and making sure things are accounted for, which includes everything from building your own little IoT devices and installing them, writing the code for the electronics, to doing the large scale remote sensing and analytics and machine learning.
Yeah.
Yeah, and also, so we are actually a subsidiary of a bigger company, and they also have some vertical farming projects. And another project is to use machine learning and data analytics to sort of improve the yield of vertical farms in very artificial, non-natural environments, to like really ramp up the things you could do there. Again, it's a lot of like both IoT, machine learning, data science, geoscience. Some of the courses that I took way back when at UCI with like soil science and whatever, like it all comes in now. It's like, oh, okay, I know a little bit about that.
Right.
Yeah, it's we're still, I mean, we just got started about a month and a half ago, so we're still kind of exploring a bunch of different directions. Maybe if I give another talk in a year or two, I can tell you much more concretely what we're building. But
Yeah.
it's it's still work in progress. But I'm excited. It's nice to wake up and like think of a new problem and talk to people every day.
Right. Yeah, and
I don't know if that was a good answer, but it's kind of up in the air.
That's the honest thing.
Yeah,
but it seems like a perfect time, right? Because like you say, there's going to be gluts of data and all these things, right? I mean, it's getting so cheap to collect the data.
Exactly.
The whole bottleneck is processing, yeah, and doing marketing, yeah.
And especially when it comes to outside of academia, like a lot of the very traditionally high-tech areas, like if you go to I don't know, like any of the high-tech areas you can think of, everything is already like optimized to the max, top of the line. If you go to any of the like more environmental things, everything is a lot more old school, right? When it comes to waste, nobody cares. It's a bunch of people that have been in the business for 60 years and they still just like have a fleet of trucks that go out. there's so much more room for like somebody to come in and revolutionize that field. But if you go to like tracking ads for Google, there's like
Yes.
you could maybe make like 0.1% difference in what they do.
Right.
Yeah, so it's on the motivational side for students on the call. I think that's something to think about as well.
Yeah, it's sort of wide open country for
Exactly.
development. Yeah.
A
Okay.
quick question. How cost effective was to run the stuff on Google's Colab using the GPUs? Was it expensive?
Yeah, no, so it was actually free because they give you free access, but only for a certain amount of time, and then it dies. But I'm always saving the last checkpoint anyway, so whenever it dies, I just go do it again. If you have the patience, you can do everything for free, which also comes in handy when you have a startup. But yeah, I just
You think is feasible to advertise that for academics, for researchers in physical sciences to use?
I think so, because I tried to do this on Green Planet, and I mean, I don't know if it's changed since when I tried to do this, but there's only 2 nodes on Green Planet. I think it's like the M0C1 and 2 or something. Those are the only ones that have GPUs, and they're so old that the CUDA version just wasn't compatible with any of the Python modules. It's like it doesn't work basically. So anything CPU based, there's so much good resources on campus, but GPU, unless you're like in computer science and your own lab has something, it's tough. And I think Google Colab, just make sure you save the checkpoints because it could just die. Save the checkpoints, and worst case, you restart it from the last place.
Yeah. And did you use PyTorch on that?
No, it was Keras, and then some fine tuning with TensorFlow where needed for like making my own cost functions and data generator classes for fitting in data and stuff. But yeah, TensorFlow and Keras all combined.
The new TensorFlow, the 2.0?
Sorry, what?
The TensorFlow 2.0 that you used?
Yes,
or
yes,
the
yes.
other?
Yeah, 2.0.
Yeah.
I believe.
I understand it has better integration with GPUs.
It does, yeah. So that part is also, it's very easy to set it up also with Google Colab. I at some point I had like my own machine at my friend's house, and I tried to do it on his GPU, and like sometimes even setting that up with CUDA and everything else might be a little hard for someone who's not in computer science. That's the other advantage for like someone in like chemistry or earth system science or whatever you say. It's just plug and play in Google Colab. So, and yeah, TensorFlow 2.0, very easy. It all sets up itself automatically.
And it looked like in your talk, almost everything you did was using basically off-the-shelf algorithms, right?
Yeah, basically.
Combining them in the right way, yeah.
Just tweaking things here and there, like if the parameters are too much, maybe like kind of get away with like, just like depth-wise convolutions, kind of like do this. But at the end of the day, it's like the first one was basically unit more or less. Second one was DFLAP v3 plus more or less. Yeah.
Great. Any more questions? If not, let's thank Yara again, and yes, let's maybe plan to have him back a year from now. Once he's rich, right?
Yeah.
You can come back poor, no problem.
I'll do my best to come back.
Okay, that was great, Yara. Thank you very much.
Okay, well, thank you very much.
Yeah.
Thank you again. Yes.
Thank you. Bye.
Bye-bye.